Okay, so welcome to last day of our this mini course. Till yesterday we were able to define Gröbner basis and all related things. Now we are moving towards how to compute that. Yesterday we finished at defining this S polynomial. This S polynomial just used to cancel out the leading monomials of two polynomials, and we'll use that S polynomial to compute the Gröbner basis of given ideal. So that was the Buchberger criteria which we discussed yesterday, and that Buchberger criteria states that if you have some Gröbner basis G and term order, then their following are equivalent. The number one is that the Gröbner basis G is a Gröbner basis, and then you have a collection of polynomials, and you take all possible pairs of those GIs, those polynomials from that collection, and you compute S polynomial for each of that pair, and then you reduce it with respect to G. If it goes to 0, that means the original set is actually a Gröbner basis. So this is Buchberger criteria. So on the basis of this criteria, there is Buchberger algorithm, and that algorithm is defined as follows. In this algorithm, the input is a set of polynomials f1 up to fs, and then all of those fi's are non-zero. And what is the output? Output is some set G, which is actually a Gröbner basis for the ideal generated by that original given set of polynomials. Okay, so just to go through from this criteria, what we do, we first take a collection of all possible pairs of given set F. Okay, and that's we denoted by this S. And how to move in the algorithm? So as soon as the that collection of pairs is non-empty, we will choose a pair from that collection, and we will remove that pair from the original collection, and then we have to compute S polynomial, and then after computing S polynomial, we need to reduce it with respect to original G. And if the after reduction, if the remainder is non-zero, then we'll place that remainder, which is written in the form of H here, we'll place that remainder in the original set, and we have to add all new pairs using that H. Here one thing is important, that once you use some pair, then you don't need to compute for that pair again. And this process will continue unless you get all remainders to be 0. Once all remainder is 0 of those pair of S polynomial, then you'll get the Gröbner basis. So let's compute one example before doing to further discussion on this Buchberger algorithm. So here is the example. In that example, we are given with two polynomials, namely we have this f1, and that f1 is given by x1 x2 minus x2, and then we are given with f2, and that f2 is minus x1 minus x2 square, and we are in lexicographical ordering with x1 is greater than x2. Okay, so we need to compute Gröbner basis for this given set of polynomials. So just to apply that algorithm one by one, what we have in this case, in the given set, there are only two elements. There is only one possible pair, and that possible pair is f1 f2. So we need to first compute S polynomial for this possible pair, and that is S of f1 f2, and by our yesterday's definition, we can compute it by first computing the LCM between their leading terms. So here x1 x2 is the leading term, here x1 is its leading pair, and when we compute its LCM, it will give us x1 and x2, and we need to divide it by leading term of f1, which is x1 x2, and we need to multiply it with f1 minus, we have same LCM x1 x2, and we need to divide it by leading term of f2, which is x minus x1, and we need to multiply it with f2. By doing so, we get this 1, and we have this x1, x2 minus x2. Here we get this negative, it give us plus, and we have this x2, and we multiply with minus this, so I get minus x1 x2, and then we have this minus x1 x2 cube actually. Okay, so now this, as by definition of S polynomial, there must be cancellation. So in the end, to write it in the form of ordering, with this that get minus 2x2 cube and minus x2. Okay, now we need to divide it with this set f1 f2, but you can see that this polynomial contains only variable in x2, and the leading monomial of f1 contains x1 x2, and leading monomial of f2 contains minus x1. So that means we will not be able to get any leading monomial which divides the leading monomial of this new S polynomial. So that means it will go to remainder r, and it will go to remainder r. That means the remainder is not 0, is not 0, and what we need to do, that we need to, by applying the Buchberger algorithm, we need to add this new polynomial in the set of polynomials f1 f2. So we can rename it as f3, and now our original f set becomes f1 f2 f3. But here one thing is important, which I told you before, that since we have already make calculations on f1 f2, then we don't need to compute it again. So in our set where we have this all possible pairs, it will be only, there will be two new pair. One is with f1 and f3, and the second pair is f2 and f3. So now we need to compute S polynomial for f1 f3, and we need to compute S polynomial for f2 f3. Okay, after computing this S polynomial, we need to divide it with this f1 f2 and f3. So let's compute it. So okay, we have this new f3 now, and that f3 is minus x2 cube minus x2. So now we need to compute this S polynomial of f1 f3, and now in f1 the leading term is x1 x2, in f3 is x2 cube. So the leading term, in the LCM of these leading terms would be in this case x1 x2 cube, and we need to divide it with x1 x2, need to multiply with f1, and minus we have same x1 x2 cube, and we now need to multiply with x3, and we need to divide with leading term of this f3, which is minus x2 cube. So we have this x1 cube x2 cube, the first term, and then we have this minus, it will give us x2 square, so minus x2 cube, minus we have this same x1 cube x1 x2 cube, and we have this minus with x2, we have this x2 x1, so this is x1 x2. And yes, so we have same cancellation, and we are left with minus x1 x2 minus x2 cube. So you can check after when we divide it with this set f1 f2 f3, after multiple steps we will get a 0 there. Okay, and again now it's 0, so we don't need to add any new polynomial in this pairs, and what is left with, we have to check for S of f2 f3, and you can check that by doing so. it will give us a polynomial, and when we will divide it, it will also go to 0, goes to 0. So we started with these two polynomials. We compute its S polynomial, we reduce it, and we get a non-zero remainder, that is F3. Now, as per Buchberger algorithm, we have to add that F3 into new set, and then we make all possible pairs. By adding this new F3, we get F1 F3 and F2 F3. With that F1 F3, we get some polynomial, S polynomial, we reduce it, it goes to 0, and also with this F2 F3, it also goes to 0. So that means in the collection, all pairs are gone, so collection is no more there. So output, what is output? Output is this F1, F2 and F3 is the Gröbner basis for the set. F1, F2, F3 is the output, is Gröbner basis for the ideal generated by F1 and F2. This is how we can apply this Buchberger algorithm to compute Gröbner basis of given set of polynomials. So in this example, there were only two polynomials. If we have like 3 polynomial, 4 polynomials, we have to make all possible pairs and then repeat this process again and again. There are a lot of softwares available which can compute Gröbner basis. It's on Kova as well, Singular as well, Macaulay too, and there are many other software related to commutative algebra who can compute this Gröbner basis after applying this algorithm of getting it again and again and again. Okay, now getting back to theory again. So this is what about this calculations. So the first thing is we need to check that this Buchberger algorithm is actually terminates and it is correct. Okay, so terminate means that after a certain steps it will stop, and correct means the output we get is definitely the Gröbner basis of the given set. So okay, so we defined this algorithm, we applied it on some example, and now we are going to see its validity. We're going to show its validity. So the first thing is to show that this algorithm stops. We suppose that it does not terminate. So if it does not terminate, that means we have infinite many iterations where we can add a new element in our G. Okay, so each times you get some non-zero remainder and you add it into G, and then you have a lot of new pairs. So in doing so, what you get, that you have this in adding each element. Suppose that you add this Gi to the set after when you have added after ith iteration. So we call it as Gi. So then you have this G1 contained in G2 is contained in G3 and so on. So this is strictly increasing because each time we are adding some new element in there. And now since this the remainder is non-zero after dividing with the previous set, so we are adding Hi in the set which is collection of all polynomials, and we denoted it by Gi minus 1. So we add Hi in the set Gi minus 1. That means when we divide that S polynomial with respect to this Gi minus 1 set, that means we are getting a non-zero remainder. Non-zero remainder means we are getting a new polynomial. So what we do, we just have in each step we compute its initial ideal, and ultimately while adding a new polynomial there, the new initial ideal will not contain in the previous one. So we ultimately have this chain of initial ideals. The initial ideal of G1 is contained in initial ideal of G2 is contained in initial ideal of G3 and so on. So that means we have a chain of monomial ideals, initial ideals, which, and this chain will not stop if we assume that this algorithm does not stop. So we take M to be union of all those initial ideals, and what we get by Dixon's lemma, that this M1 and Mi's are there, this union will be definitely generated by some finite many monomials. So by Dixon lemma says that any collection of monomials has a finite many minimal element with respect to divisibility, or you can say that every monomial ideal is finitely generated. So that means this collection is a collection of monomials being generators of initial ideals. So that means we must have a finite set which actually generates which generate all that union. So now we have a chain, and in that chain, the union of chain, we are saying that there is a finite many sets who actually generate all elements in that chain. That means if we put one element one by one in that chain, there will be we can find an element where you can see that all monomials will be within that limit, and we call that limit to be I prime, that there exists some I prime such that all those M1 up to M are actually union of elements up to I1, that the chain start with 1 and you end up with I minus 1. All those monomials will be in that limit, and in doing so we have this initial ideal of that Gi is actually Mi, but it also correspond to all elements which are coming afterwards. That is a contradiction, because this is a chain which is strictly increasing, so that cannot happen. So that means our assumption is wrong, that it's does not terminate. So that means the chain must terminate at somewhere. Now to show that since we have this termination of the algorithm, now we need to show that actually what we are getting in the end, it's actually a Gröbner basis for the ideal, for the set, for the ideal generated by given set. Okay, so at that point we use that Buchberger criteria, that all S polynomial reduced to 0, so we are getting this Gröbner basis. Okay, so that means we have correctly defined this Buchberger algorithm, but still after saying so, we still need to show that this Buchberger criteria we haven't proved yet. In the next we are going to prove, or going to see the proof, some ways to prove this Buchberger criteria. So let's moving ahead. This is the result, that if you are given with the set of generators G1 up to Gs, then and we have fixed a term order, then the following are equivalent, that G is a Gröbner basis and all S pairs of those Gi's goes to 0 after we reduce it with respect to original set G. Okay, so that the criteria we need to show. But before proof of this Buchberger criteria, we need another result, and that result states that we have some sets F1 up to Fs, and that set is a collection from this polynomial ring, and we have a term order, we have a fixed term order such that leading monomial of F1 up to Fs is equal to some monomials, and we say that this F is a linear combination of S polynomials Fi Fj, that we are going to prove. So the result states that let F1 up to Fs be set of polynomials from polynomial ring such that we have an F which is summation I from 1 up to S Ci Fi, where this Ci belongs to some field K, and we have a fixed term order, and we say that leading monomial of F1 is same as leading monomial of Fs, and which is some x alpha, and of course we have a such combination such that leading monomial of this F is less than this x alpha. That means since the leading monomials are same, so that combination is like that it cancel out the leading term. So what we get after cancellation of leading term, we get a new leading term which is less than the original leading term. Okay, so then we say that F is a linear combination of S of Fi Fj for all 1 is less than I less than j less than equal to S. Okay, that we are going to prove. All right. So we have some this each Fi is of the form some Ai and some X alpha, which is same for every Fi, but it has different coefficient. And then we have some lower terms. So we define this S of Fi Fj to be, in this case, we have same LCM for any all monomials, all polynomials, because all polynomials have same leading monomial. That's our assumption. So that is why we have this S polynomial, in this case 1 over Ai times Fi minus 1 over Aj times Fj, because this LCM and this monomial is same in this case. That's why we are getting this 1 over. So each S polynomial is of this form. Okay. Now we have this F, which we define to be a linear combination of this F1 plus FCS where this Ci is elements from some field K. So that means we can write it, we can define, okay, C1 A1, and we multiply with A1 and we divide with A1, and we have this F1 same and so on, CS AS over AS FS, and we can add and subtract the next term to get our required combination in the form of S of Fi Fj, because it means we have 1 over Ai Fi minus 1 over Aj Fj. So we can add subtract terms and we get C1 A1 is equal to 1 over A1 F1 minus 1 over A2 F2, and we have to add this same C1 A1 minus 1 over A2 F2, and we get this plus C1 A1 plus C2 A2, and we multiply it with 1 over A2 F2 minus 1 over A3 F3, and this process will continue, and in the end we have so many factors of the form CS minus 1, A S minus 1, and we multiply it with 1 over AS minus 1 FS minus 1 minus 1 over AS FS, and finally we have this plus 1 over C1 A1 plus so on plus AS FS, and we multiply it with simple 1 over AS FS. Okay, so so we just add and subtract terms just to make sure that each we have factors like this. Now each of these factors represent S of F1 F2, S of F2 F3, and so on. So ultimately we get C1 A1 S of F1 F2 plus so on, and we get in the end that C1 A1 plus so on plus C S minus 1 A S minus 1, and we multiply it with S of F S minus 1 F of S. Okay, so we have all this F in the form of this combination which is have this S of combination in the form of S. So that's what we need to show in this result, that if what is the main thing, that if you have same leading monomials, in that case if leading monomials can be if leading monomial cancelling out in that combination, then we can write that combination in the form of combination of S polynomials, because that lemma we will use in the proof of Buchberger criteria. Okay, now we have to show this Buchberger criteria that first we suppose that G is a Gröbner basis, and we need to show that each S of Gij is reduced to 0. To prove this, we have this effect that G is a Gröbner basis if and only if we can write this F and in the form of F, this combination H1 G1, and ultimately by applying so we have this on this direction that if G is a Gröbner basis, then each S polynomial is a combination of G1 Gi's, and ultimately it will goes to 0, since we all have the supposition that each of Gi Gj is the part of Gröbner basis. So this direction is trivial, more trivial. For the converse part, you can just go through from these slides. All proof are written there, and you can check that if I'm not going through the converse part, but all converse part is written over there in these slides. You can have a look in proving this Buchberger criteria. Now we are going to define the with this the Gröbner basis we have defined, and we have shown this Buchberger criteria, and also we computed for one example, and we also just prove one part of the Buchberger criteria due to this being a mini course, but the converse is already there. You can just go through from the slides. If you have any question, you can write to me as well. You can find my email ID from this COMSATS University Pakistan homepage website. Okay, now we are going to define next thing, which is a minimal Gröbner basis. So what is minimal Gröbner basis? Minimal Gröbner basis means we have a Gröbner basis, and in that Gröbner basis, if no leading monomial of each of its element divide with each other. So you see, when we applied that effect of Buchberger algorithm, we are each time we are adding some new polynomials. Okay, so by adding a new polynomial, there is a chance that maybe there are few polynomials whose leading term may divide each other. So what we need to do, we need to just remove the one whose leading monomial divides the other one. Okay, so we need to remove that whose leading monomial is divisible by the previous one. So that means we have to remove the larger element, so that the initial ideal will remain the same. It does not matter because if you have so let's say you have an ideal Gröbner basis of the form F1 up to Fs. So if it is a Gröbner basis, so by definition initial ideal of I is given by this leading monomial of F1, so on, leading monomial of Fs. Okay, so if we say that there are say two polynomials whose leading monomial divides each other. For example, if I say that leading monomial of Fi divides leading monomial of Fj, then in the definition of monomial ideal, if this divides this one, then actually we do not need that monomial to be there, because we always take minimal set of generators. So if we don't need it in the definition of initial ideal, then actually we don't need that polynomial to be there as well. So we have to delete all those Fi's whose leading monomial is divisible by some other leading monomial. So if we do so, the new Gröbner basis, the new set we obtained, we call it as a minimal Gröbner basis. So this is one form of Gröbner basis which we call it as to be minimal. Then there is another form of Gröbner basis. Okay, well, one thing I forgot to mention, that for the Gröbner basis you have an algorithm, and you apply that algorithm by having all possible pairs on the S polynomial. Okay, so you choose one pair and you compute its reduction, reduce it. If it is 0, well and good. If it is not 0, you put it in the loop again to compute this Gröbner basis. So maybe by doing so, it's all depend upon the selection of the pair. So if you change the pair, maybe you get some different remainder. So the summary is that the Gröbner basis is not unique. For using this Buchberger criteria, Gröbner basis can be different. Okay. This minimal Gröbner basis, this is also not unique, but what is unique in Gröbner is in the minimal Gröbner basis, the unique part is that you always get number of, if you have two different minimal Gröbner bases, the number of elements in one basis will be same as the number of elements in the second basis. So this is unique in the form of number of elements. So Gröbner basis is not unique for any ideal, but minimal Gröbner basis is unique in the sense that it can two different minimal Gröbner bases may contain same number of elements, in the Gröbner basis. But what is unique? The unique part is that a Gröbner basis is unique if it is reduced Gröbner basis. So what is next? Next is definition of the reduced Gröbner basis. And what is reduced Gröbner basis? A reduced Gröbner basis is that first it is a Gröbner basis, second it is also minimal Gröbner basis, and third part is that no term in any part of G is divisible by any of the other leading monomial of Gi's. How? That if you have this Gröbner basis G, so this is a reduce, it is a reduced Gröbner basis if number one it is minimal. Minimal means you have to remove all those fi's whose leading monomial is divisible by any of the leading monomial of other fi's, fj's. It should be minimal. And the second thing is no term in any fi is divisible by any of the leading monomial of the other one. And if not divisible by any of the other leading monomial, that means we are actually reducing it. This is the process of reduction, that when we divide it, we get all those in the remainder, those terms which is not divisible by any of the leading monomial of fi's. So no term in fi is divisible by any of the leading monomial of fi for all I other than for all okay, let's say j, for all j where j varies from 1 up to s, and you subtract this I from this. Okay, so other than that all is reduced. So now how to find reduced Gröbner basis? So first you need to find minimal Gröbner basis. That minimal Gröbner basis means you just need to remove fi's whose leading monomial is divisible by any of the other fj's. And then what you need to do, you need to first step, you need to divide this f1, you need to reduce it with respect to f2, fs, and suppose you get this h1 as a reduction. And by definition, when we have this notation, that means this h1 will not contain any term which is divisible by any of the leading monomial of this f2 up to fs. In the next step, you will apply this f2, same thing, but now you are going to divide it with this h1, f3, so on, fs, and you get this new h2. Again, this h2 will not contain any term which is divisible by any of the leading monomial of this set. And this process will continue. And in the end, you have this fs, and you will divide it with h1, h2, so on, hs minus 1, and you get this hs. Okay, so now this all hi's on this right hand side will not be divisible by any of the monomial of these fi's, and this means this h1, h2, hs is reduced Gröbner basis. And this is reduced Gröbner basis means that for any ideal, this reduced Gröbner basis is unique. Okay, whenever you have an ideal, then it always has a unique reduced Gröbner basis. So this, at this point, we are going to answer our questions which we have posted on the first day of lecture. The first question was that if you are having two systems, so if you are having two systems, say f1 equal to 0, so on fs is equal to 0, and another system g1 equal to 0 up to gt is equal to 0. So the question was whether an ideal generated by fs is same with respect to ideal generated by gt, or suppose we are getting this system from some physical problem and we need to show that after certain steps we found some solution of in this form, and we need to check whether we are having the good solution or same solutions. So what we need to check that whether we put those system in the form of this ideal, and we need to check whether these two ideals are same or not. So the answer is the following: since this combination has a unique Gröbner basis, and this combination also has a unique reduced Gröbner basis. This is having a unique reduced Gröbner basis, and this is having a unique reduced Gröbner basis. So we compute reduced Gröbner basis for this system, and we compute reduced Gröbner basis for this system. If both are same, that means that both ideals are same or both systems are same. But if we are getting different reduced Gröbner basis, that means this system are not same. So this is the answer of first question, that whether two given system represents same solutions or not. Okay, so this is answer to our first part. The second part was that we are given with this ideal membership problem, that we are given with f, and whether this f belongs to a set of generators or not. Okay, whether it belongs to some certain ideal or not. So what we need to do in that case, even the Gröbner basis will work for us. We don't need to compute even reduced or minimal Gröbner basis. Because what was the problem? The problem is the following, that when we divide it with some set of polynomials, we are not getting a unique remainder. But in the form of Gröbner basis, we have already proved yesterday that we always find a unique remainder. So we will have this f, we will have this f1 up to fs. We need to check whether it belongs to this set or not. What we will do, we will compute its Gröbner basis first, just to make sure that we are getting this right thing, and then we have this f. Suppose the Gröbner basis is g1 up to gt, and then we divide this f with this g1 up to gt, and if the remainder is 0, that means that belong to f will belong to that ideal, because Gröbner basis and ideal represents the same ideal. So if we have this Gröbner basis and we have original ideal, so both are actually equal in this case. So if f, we divide this f with the g1 up to gt, and we get a unique remainder which is 0. If it is 0, then f will belongs to I. If it is not 0, then f doesn't belong to I. The last part of last question we mentioned was that what are the factors that this f is equal to u1 f1 plus so on plus us fs. Okay, we are dividing this f with g1 up to gt, and we are saying that okay, after dividing the remainder is 0, but we are not dividing this f with f1 up to fs. But what is our requirement? That what are the factors we multiply with f1 to get this u1 and us in the form of this f. Okay, so what we will do, you can see that in each of the factor of this g1 and gt, we first computed s polynomial. The s polynomial was a combination of some factor with fi and then some other factor with fj. So that was the formula for we used to compute s polynomial. So s polynomial in principle is a combination of fi and fj. and then what we did, we divide it with that set of fi's. So again we dividing it with fi means ultimately this factor will be combination of, by reverse calculation, will be combination of fi's, and then if that is non-zero, we call it as a new factor in the Gröbner basis, let's say gi. So ultimately any element, this g1 gt is actually a combination of fi's by that reverse calculations. Maybe some gi's are exactly equal to fi's, and maybe some gi's which are we obtained by getting that non-zero remainder will be some combination of fi's. So by having this reverse calculation, we can find, we can get this fi's from this combination, from the combination of u1 prime g1 plus so on u t prime gt. From this combination we can get this required combination which is in the form of original generators. Okay, so this is how we answered to all our 3 questions. Now this is about this is all about Gröbner basis, minimal Gröbner basis and reduced Gröbner basis. So I think this is a good point to have a short break, because now what we are left with, some applications of Gröbner basis that we can do after the break. Okay, so let's do the final part of this course, in which we will see few applications of Gröbner basis. There are plenty of applications of Gröbner basis which you can find through internet. If you simply write application of Gröbner basis, there will be number of articles which give you a lot of applications of this theory. We will focus on maybe 3 if we can do that. One we will do for purely algebraic way, that if we are given with 2 ideals, any ideals, then how to compute its intersection using this technique of Gröbner basis. As far as monomial ideal is concerned, you simply compute its intersection by computing your respective LCMs, but in case of this polynomial ideal, we will use this technique of Gröbner basis. Secondly, we will work on to find a kernel and image of a polynomial map using this technique of Gröbner basis. And also for the last part, we will see some its application for I'm just checking that if my mic is working. So for the third thing, we will see that if how to have 3 coloring of a given graph by using this technique of Gröbner basis. So we'll do these 3 applications, but to have these applications we need some terms, we need some definitions, so that we can apply this technique over there. Okay, the first thing is about this variety thing that I will discuss a little bit later. But now firstly I would like to define this ordering, which is elimination ordering. In that elimination ordering, you have 2 set of variables. You have x variables and you have y variables. Okay, and then when you have 2 variables, then you have 2 types of, you have in your each monomial you have you can have 2 part. One, you separate the x variables and then you separate the y variables for one monomial and for the second monomial as well. Okay, and then we say that this product of x variables and y variables are less than if and only if either x variables, first check with x variables and then we check with y variables. So let's do it on the board. So we have some x variables and we have some y variables, and we have some ordering, say ordering 1 on x variables and ordering 2 on y variables. Then we say that x1 y1 is less than x2 y2. So this is the monomial having both x variables and y variables. Similarly, this is the second monomial having this x variables and y variables. We say that this product is less than other product if and only if we have either x1 is less than x2 with respect to the ordering on x variables, or if x1 is equal to x2, we must have this y1 is less than y2 with respect to this second ordering which we define on y2. So this ordering is called elimination ordering, but here we have given preference to x variable. So we say that this is elimination ordering with x variables larger than y variable. Okay, so you can check, this could be your assignment, that you can check that this elimination ordering is in fact a monomial ordering. So for monomial ordering, you have to check that each we can compare any two elements, one is a least element and is compatible with respect to multiplication, so that you can check that this elimination ordering is actually a monomial ordering. Moving ahead, this is a result which is quite important, that we can use that result, and this result states that let I be a non-zero ideal in the polynomial ring K of yi's xi. So we just have xi's and yi's two variables, and let this less be a elimination ordering with respect to x variables larger than y variables, like the way we just defined that we are giving preference to x variables, and then if x variables are equal, then we are checking towards the y variables. And let G be a Gröbner basis of the given ideal I, which is in both x and y variables. Then the result is, then G intersection K of y1 ym is the Gröbner basis for the ideal I intersection K of y1 up to ym. So what does it mean? It means that you have an ideal I which is in both variables x1, x2, xn and y1 up to ym, and you want to eliminate x from this ideal. Eliminate x means like when you are solving some system, and to solve that system we use this elimination process, that we eliminate variables one by one. So this result will help us to get some variables eliminated. So how? Because how we can do that? We first need to compute Gröbner basis of this I with respect to given elimination ordering, and then when we have Gröbner basis, that means we have a set of polynomials. Okay, and when we say that G intersection K of y1 up to ym is a Gröbner basis of I intersection K of y1 up to ym, so that means we are eliminating this x variables, from that ideal I. So I intersection yi means we are having only x variables. And how to do that? We have not in that, this is ideal, it's not easy to take, ideal has infinite many elements, so we cannot take directly intersection from here. But here this G is just a finite set, is a set of basis, because by Hilbert basis theorem any ideal is finitely generated. We already computed Gröbner basis, so it is also finite. So we have a set there, and on that side we have a polynomial ring. So we need to see only those elements which are having only y variables. If there are x variables, that cannot be in the intersection. If there are mixture of x and y variables, that cannot be intersection in the intersection. So we need to have only those polynomials which are in this having the elements or monomials from the y variables only. So by doing so, we can eliminate all x variables. But for that, what we need to do, we need to define an ordering in which x variables are larger than the y variables. So we are giving preference to x variables, and then we see that okay, by doing so we can eliminate these x variables from this section. Now this we will use this elimination. We will use this elimination process to find intersection of two ideals. Okay, so this result states that we have two ideals I and j, which is in k of x1 up to xn, and let w be a new variable. We will introduce a new variable w there, and we consider an ideal which is w time I and 1 minus w times j. And now this new ideal is actually in polynomial ring with n variables, and we are adding a new variable w there. So it is polynomial ring x1 up to xn, and then there are w as well. And then the result states that intersection of I intersection j is nothing but w times I, 1 minus w times j, and then intersection k of x1 up to xn. That means we have we have I intersection j is equal to w times I, 1 minus w times j, and we are taking intersection with k of x1 up to xn. So it means that we have to eliminate w there. So we have to define an ordering in which w is larger than the x variables, and then we need to compute Gröbner basis for this new ideal. And this new ideal is simply, let's say I is generated by u1 up to us, and j is generated by say v1 up to vt, and then this wi is u w times u1 so on w times us, and 1 minus w j is you need to multiply 1 minus w with each of this generator v1 up to 1 minus w times vt, and this new ideal wi with 1 minus w j is actually will be generated by w u1 up to w us, and then you have this 1 minus w times v1 into 1 minus w times vt. Here this u1 and ui's and vi's are actually polynomials. These are not monomials, these are actually polynomials, and we can compute this ideal, and then we need to compute its Gröbner basis by taking w larger than the x variables. So once we get that Gröbner basis by using techniques or some online softwares, or from using some softwares, what we will get, we'll get a new Gröbner basis, and then we need to have intersection of that Gröbner basis with x1 up to xn using our previous result. So we just need to compute its intersection with the x variable. So we need to have only those variables which only those polynomials which are in only x variables, and those polynomials will give you Gröbner basis for I intersection j. And you know that if you have a Gröbner basis, that means it generates the same ideal. So I intersection j is nothing, just you have this generating w Gröbner basis in the form of generating set. So this is how we can compute intersection of two ideals using this technique of Gröbner basis and using this elimination ordering. So this is one application of Gröbner basis which we have just discussed. And now this is an example. Example is already available on the slides. I think we have a bit shortage of time, so you just go through. In that example, you're given with the ideal I, which has two generators. You have ideal j, which has one generator, and then you define this w times I and 1 minus w times j. Then you computed its Gröbner basis using software, some algebra softwares, and then you have this its Gröbner basis for, and then when you are taking with only I intersection j, then it's in x and y variables, and you eliminate w variable, and then you have all these factors which will give you intersection of I intersection j. Okay, next on the slides there are given that we can also compute quotients of two ideals. So how do we define quotient of two ideals? I quotient j is defined as those polynomials from k of x1 up to xn such that the g times I is contained in j. So this is the definition of quotients of two ideals. So again, when we need to compute quotient for the monomial ideal, it is quite simple. You can compute it by finding GCD, and then there is a calculation. There are results which help us to compute quotients of two ideals. But in the case of polynomials, we'll use this technique to compute quotient of two ideals. And on the slides you can find all method how to apply those method to get quotients of two ideals. So the results are there, proof is there, and also one example is there. And now coming to our next thing, which are second application. And second application, as I told you before, it is about finding kernel and image, or to check whether given polynomial map is onto or not. So we can use Gröbner basis to see all these possibilities to how to find the kernel or all those stuff. So before that, we just need to define a little bit about polynomial map. So we have a map, say phi, and that map is from k of y1 up to yn, and it is from k of y1 up to yn to k of x1 up to xn. So it is from y variable to x variables. And for polynomial maps, for this polynomial homomorphism, we just need to have images of variables from the domain. Like we should know that this yi map to which function of xi for each yi. So this function is not only in xi, this function is from x1 up to xn. So we need this information for all I varies from 1 up to this n. Okay, so we need that information. Here are from y1 to yn, and x variable say x1 to xm. So we need only this information. Once we have this information, that is sufficient to see the properties or all properties of the given map. So for example, if you have this phi from k of y1, y2, y3 to k of x1, x2, then we simply need that what is y1 map to, y1 is mapped to say x1 plus x2, y2 say map to x1 square, and y3 say map to x2 square. So we need only this information in this case, and we can find image of any element by using this information. So this map defined this polynomial ring. So next we need to see that how to compute its this given the map is what is the kernel of that map. For kernel of this map, we will use this result, and this result states we will how to find its kernel, and for the kernel we will use this result, and this result states that we have a map phi from y variables to x variables, and indeed it is given by some images of yi's. And what is for kernel, we defined a new ideal. Let me have it on the board again. So we have a map phi from k of y1 up to ym to k of x1 up to xn. Okay, so in the previous example we are taking n y variables and mx variables. Now my variables or it doesn't matter, it's just matter of notations. And we define it like yi is mapped to some function of x1 up to xn for all I varies from 1 up to m. And then we define a new ideal, and we call that new ideal to be this k, and this new ideal is y1 minus f1. So yi is mapped to fi, so we define y1 minus f1 and so on ym minus fm. And now this ideal has y variable from the domain and f variable from the range, that means k of x1 up to xn. So this new ideal will be from the polynomial ring k of y1 up to ym to x1 up to xn, and the result states that the kernel of this map is nothing, just you need to eliminate x variables from this ideal. So you need to eliminate x variables from that ideal, and this ideal is in both x and y variables. And kernel means we are looking for elements from this k of y1 up to ym. So when we compute this elimination, the elimination we can use the same way which we have computed before, that we compute Gröbner basis with respect to x variables larger than y variables, and then we just need to eliminate those polynomials which contain both x variables or x and y variables. So we need only those polynomials which are only in y variables, and then that will give us this intersection, and that intersection will give us that what is the generating set for this kernel of y. So this is how we can compute kernel using this technique of Gröbner basis. So the proof of this result is there, and also yesterday I mentioned that some part of this lectures are from an introduction to Gröbner basis by Adams. It is a book from AMS, so you can find it, or in that book we use some results for that for this lecture. So proof of all these stuff you can find there as well, and I have written in these slides as well. So the next statement states that if we want to check that whether a given polynomial belongs to image of the map or not. Okay, so so image means we want to check that whether a polynomial from x variables exists any polynomial in y variable, so that we can apply map to get that element from the x variables. So like in the previous case, the definition of the map is same, that we have from y variables to x variables, and then we define this same k, and the result states that. So this is the second result about how to check whether a given map belongs to or not. So we have this map from y variables to x variables. We defined it from y to fi's, and we define this new k. Then we say that f belongs to this xn. So this is a little bit, okay, this k is an ideal, and we have this simple k as a field. So is in the image if and only if there exists some h belongs to k of y1 up to ym such that f is reduced to g with respect to this g, and this g is Gröbner basis for this ideal k. So what you need to do in this case, you have to compute Gröbner basis for this k, and after computing Gröbner basis, you want to check whether f belongs to image or not. So you need to divide that f with using that g, and after doing so you get a remainder h. Okay, so if that remainder is only in y variables, if that remainder is only in y variable, there is no x variable, no more x variable, then we say that that f will belongs to the image, and in that case that phi of that h is actually equal to f. Okay, so this is how we can check that whether a given element, given polynomial belong to image or not. Not only this, but also we find exactly that element to which we apply phi to get that particular f. So this result is also there, its proof is there, you can go through, there would be some example as well. So again, with that, we are done with the second part of this polynomial map, and this is the result for the third part. For the third part, we'll have the result which states that by using the same settings, we can check whether given map is onto or not. So this is the third part. So for the third part, we say that this phi is onto if and only if for each I varies from 1 up to n, there exists some elements gi belong to g such that gi is equal to xi minus hi, where hi belongs to k of y1 ym. Okay, so we are given with the map. That map is defined by yi's goes to fi's, and we define this k on the same way we defined before, that y1 minus f1, so on ym minus fm from this polynomial ring in both y and x variables. And then we compute Gröbner basis for this g, again by taking x variables larger than y variables like we did before, and we say that phi is onto if and only if for each variables from x1 up to xn, we get a factor in g, and that factor is of the form xi minus hi. So that means if, for example, we have say map from y1 up to y, so say we have map from k of y1, y2, y3 to k of x1, x2. So what we need in the Gröbner basis of that g, so we need in g an element of the form x1 minus some function of y1, y2, y3, and x2 minus some function of y1, y2, y3. So for each of these x variables, if we can find a factor of the form that variable minus some function of y variables for each of them, then we will say that that map is onto. But if, for example, for a certain variable, if any one of them is missing, then we say that the map is not onto. So with this, we can compute, we can check that by using this technique of Gröbner basis, we can check whether how to find kernel of a map, we can check whether map a certain element belongs to the image or not, and the third one is whether a given map is onto or not. So we can, as I said before, that proof of all these are available in the slides as well, and as well in the book of Adams by Introduction to Gröbner basis, and there are some examples as well. So due to shortage of time, I'm just giving you the overview that how we can apply this technique of Gröbner basis to solve these problems. Okay, so now moving towards the last part of applications. which are actually three coloring problem. But before going to three coloring problem, I need to define variety. What is a variety in uh, so the for some certain polynomial, we define a variety of f to be those points x1 up to xn from n or r, okay, from kn is a field such that f of x1 up to xn is equal to 0. For example, variety of say x1 square plus x2 square minus 4 is can be given in the form of a circle having radius 2 and center 0. Okay. Then okay, if we want to find variety of certain ideal, and again these are collection of those points such that f of those points x1 up to xn, okay, we since we are taking elements from field, we can say okay, a1 up to an, that's better because we really call x for the variable. So a1 an, and also we need a1 an such that f of a1 up to an is equal to 0 for all f belongs to I. So this is the definition of variety, and we have a result in using the Gröbner basis that and that result states that so variety of I is non-empty if and only if so we say that we have an ideal I from k of x0 to xn. We say that its variety is of I is empty set if and only if I is equal to the whole ring, and variety is equal to also we can say that variety of that I is empty set if and only if one belongs to Gröbner basis. So when we say that one belongs to Gröbner basis, that means that ideal will be given by the whole ring. Okay, so variety is empty if and only if the I is polynomial ring itself, and we can translate same thing in the form of Gröbner basis that if variety is empty set if and only if actually one belongs to Gröbner basis. When we say one belong to Gröbner basis, that means it will the ideal will be given by the whole ring. Okay, so how to check for a given ideal whether it is empty or not? We need simply to check, we need to compute its Gröbner basis, and if the Gröbner basis contains 1, that means we say that varieties of that I is empty. There is no element, if one belongs to Gröbner basis, there is no element for which all polynomials in I is equal to 0. Okay, so we will use this result in finding the coloring of a graph. So let's move to last part of our this mini course. In the last part of this mini course, we are going to check whether a given graph is three colorable or not. So what is the problem? The problem here is that you are given with certain graph. Let's go to this graph directly. Okay, so let's say we have this graph or any graph. And suppose we are given with this graph, for example, and this is true for any graph. So what we need to check that whether this graph is three colorable or not. What does it mean? It means that can we color the vertices of this graph in a way that any two adjacent vertices, vertices sharing an edge, has different colors. Okay, so this is the problem from the graph theory which we can solve using technique of this Gröbner basis. Okay, that's what we are going to do. So I'm doing it by doing on a particular example, but this theory can be generalized to any graph. So for example, we have this graph or any graph G. So what we need to do, we need to check whether three colors will be sufficient to color all vertices so that any two vertices are having different colors. So three colors means we will assign, we will use this cube root of unity. This cube root of unity means we are looking at the solution of the equation x cube is equal to 1. So in complex numbers, we can have its solution in the form of three elements, which is called cube root of unity, which is, we suppose that 1 xi and xi square. Suppose these are its three different roots. So we refer these three roots to three different colors. Okay, so which we can assign to any of the vertices of this graph. So suppose we have its vertices, say x1, x2, x3, x4, x5, x6, x7, x8. We have 8 vertices. So suppose we assign xi's to one of each vertex there. Now we need to assign a color out of this 1 xi and xi square to any of the vertices there. So that means we can assign any color to any of these vertex. Okay, so that means we can have equations of the form xi cube is equal to 1 for all I varies from 1 up to 8. That means any variable can have any root, and each root we refer to a color. So x1 can be given 1, or x1 can be given xi, or x1 can be given xi square. Okay, so that means now it's we have random choice. We does not impose any condition yet. But what is our condition? Our condition is that if two vertex are adjacent, they should have different color. It is equivalent to saying that if x1 is given some root, then this adjacent vertices should have a different root. Okay, so that means if we have this x I cube is equal to x j cube, and this is same as that x I cube minus x j cube is equal to 0, and this is same as by saying x I minus x j into x I square plus x I x j plus x j square is equal to 0, means if xi minus xj is equal to 0, it means that xi and xj are having the same roots. But we don't want this. We don't want to have xi minus xj equal to 0. So that cannot be 0. If it is 0, that means both are having same color. And so this implies that xi square plus xi xj plus xj square is equal to 0. So this is for those xi and xj which are sharing an edge. Okay, so where this xi xj belongs to edge set of that graph. Okay, so just to summarize, we are given with a set of vertices and set of edges. to each vertex of that graph, we will assign equation like this, and to each edge of that graph, we will assign equation like this. For example, in this case, there are 8 vertices and there are 5, 6, 7, 8, 9, 10, 11, 12, 13. There are about 13 edges. So we have 13 equations of this form and we have 8 equations of this form. So what we need to do? We need to find solution of this system. The first part will make sure that we can assign any color to any variable, but this second system will make sure that any 2 adjacent will have different colors. So then we have a big system and we write, okay, suppose we call all those to be fi's and we call all those equations to be gj. Then we have an ideal I in this case, which is from f1 to f8 and then g1 up to g13. So we have an ideal which contains all polynomials coming from vertices and all polynomials coming from the edges, and we need to compute its solution. That if solution exists, if we can find a solution where all these holds, we will say that that system, the graph is having a solution of graph can be 3 colorable. But if no solution exists, then we say that graph is not 3 colorable. So we need to compute its Gröbner basis, and by our previous result we will say that this system variety of I is empty if and only if 1 belongs to this Gröbner basis G. G is a Gröbner basis of I. So if 1 is there, then we will say that no solution exists. If 1 is not there, then we will say that okay, the graph is 3 colorable. So this is how we can check a given graph is 3 colorable, not by using this technique of Gröbner basis. But this not up to here. Even we can decide colors using the form of Gröbner basis. For example, for this graph, we have already computed its Gröbner basis, and its Gröbner basis is like having factors like x1 minus x7, then it's factors like x2 plus x7 plus x8, then we have this x3 minus x7. So it has factors like this. So by using these factors, we can decide that whether we will, if we, for example, we assign some value to this x1, so we need to assign a different value to x7 and so on. So using that factors, we can also decide that which colors we should give to a certain vertex. So with this third application, which is on the graph coloring, so I think we have finished all these 3 applications which I mentioned in the start of this video, that we will go through from these applications. And also there is one more application which is in the form of integer programming. This is also available on these slides, and the main goal of this application is that we are looking for those solutions which are actually integer solutions. In particular, the solutions, the system having positive coefficients, and also we are looking for its solutions which are having these positive coefficients. That means we relate it with some power of variables. So power of variables in the polynomial rings is always positive. So using that thing, we again use Gröbner basis to solve that system. This is also there in the slides. If one is interested, that can be gone through all this. So with that, I think I'm done with this mini course. Let me see if there is some important question to answer. Okay, so it's just thank you so much for your nice comments. So if you have any question, you can write it directly to me. As I mentioned, that I'm professor at COMSATS University Islamabad Lahore campus. From their website, you can find my email ID. You can contact me. I will be happy to reply for any query. regarding to this course or any other thing you want to discuss. So with that, with these words, thank you so much. I'm signing it off from here in Nice, France. So see you at some time. Bye bye.